Thank you very much. I'm from Kyoto. Today I want to talk about the OPM application to neuroimaging. I hope you may all know where Kyoto is. Kyoto was recently selected the most attractive city to visit for sightseeing. In 2011, we have International Symposium on Atomic and Fundamental Physics and its applications, focusing on the OPM. You may know some of these persons, Professor Budka and Professor Romalis and Dr. Kim. We invited them to talk in this symposium. I guess this is the first international symposium concerning on OPM. And Professor Happer also visited our lab in 2008. This is the outline of my talk. Today, I want to talk about limitations of the current neuroimaging techniques first, and then I explain about our history of research on OPM. I first talk about the portable OPM and the MEG measurements with it. And then I'll talk about potassium and rubidium spin exchange OPM, then ultra-low field MRI using OPM. And finally, I talk about the future directions about the functional MRI and the functional magnetic particle imaging. And I'll finish with a brief summary. I think most of you are not familiar with brain or neuroscience, so I'll explain a little bit about what brain is and what the neuroimaging is. Human higher brain functions performed in our brain. Brain is a center of our central nervous system, and the human brain is a dynamic system which processes information both temporally and spatially. So an important step to obtain knowledge about dynamic neural activities, development of neuroimaging systems with high spatial temporal resolution is crucial things. Shown here is current non-invasive neuroimaging systems. In this workshop, some previous speakers talk about the OPM application to MEG, but we have different types of neuroimaging systems. None of a single neuroimaging system is not enough to reveal higher brain functions like the consciousness or language or recognition. This is a comparison of the several neuroimaging techniques. MEG is known as a high temporal resolution like EEG, while functional MRI has the high spatial resolution. So to integrate several neuroimaging techniques, we can get high spatial temporal resolution imaging system. We have been developing a novel approach of functional MRI and the MEG integration, which analyze dynamic activation multiple cortical areas. I have been involved in the field of biomagnetism more than 30 years. MEG, based on the square techniques, has a high temporal resolution, and the MRI and fMRI has a high spatial resolution, as I mentioned before. To integrate, if we can integrate both, we can know or reveal the higher brain functions. I want to talk about what the integration method of fMRI and MEG, but today I have my time is limited, so I just demonstrate what we can do by integrate the both techniques. In this case, I show the example of an appropriate apparent visual motion perception task. As you can see, we present the white circle on the upper side and switch the image to the lower part, and we repeat to present these two images alternately. We can perceive the movement, which is called an apparent visual motion perception. The image is like this. You perceive the movement, but the stimulus itself doesn't move. By review the brain mechanism of this kind of visual perception, we can measure the where in the brain is involved in the processing of this stimuli. By using the MRI, we can know the where in the cortex are involved in this task. As you can see, we can clearly detect the fourth visual cortex, but we can't tell when we can these areas activate. By using the whole head MEG system, we can measure the neuronal activities as a time resolution of 1 millisecond. By using MEG, we can tell which part activate first, and then information moves which way, or something like that. By integrate these two data, we can know in each voxel dynamic activations. This is a flow chart or pipeline of our recent integrated fMRI MEG method. I don't have enough time to explain in detail, but for example, when we apply this technique for another perception task called transparent motion perception, which is when two groups of random dots is presented on a plane and they moved oppositely, we can perceive two different planes with different depths. By using fMRI and MEG, we can tell which part of the cortex activate as a function of time, like this. If you are interested in, we published the data in the human brain mapping in 2015. Please look at the paper. So in 2006, we started a joint research project between our university and a Japanese company called Canon to develop advanced imaging technologies. Our mission of this project is to develop highly sensitive OPM towards non-invasive neuroimaging and multimodal MRI systems. Since then, we continue developing the system. So next, we would like to explain the history of our development of portable MRI. In 2012, we first published our compact OPM module. The sensitivity was 14 femtotesla per root hertz at 100 hertz. This is a good one, and we continue miniaturize the compact OPM module. This is our second compact OPM. We published this 2015. By using this compact module, we try to measure visually evoked fields. As shown here is a setup of the experiment of MEG. We gave visual stimulus shown on the right. This is called checkerboard pattern. Checkerboard flicked as a function of time, and we measure the evoked field, both our compact OPM and the whole head MEG system. These are the result. The upper row is the result obtained by OPM, our OPM, and the bottom row is a result measured by whole head squared. As you can see, we can get a good agreement. Then we continue miniaturization, and this is our third 4-channel compact OPM. I showed you in the Biomag 2016, and then this is our latest compact OPM. Now we are collaborating with a Japanese company named Hamamatsu Photonics. This is the history of our development of portable compact MR OPM. Next, I'll explain what the potassium-rubidium spin exchange OPM. This is the principle of the potassium-rubidium spin exchange hybrid OPM. We use two alkali species. In this case, we use the thick potassium atoms and thin rubidium atoms. We gave the pump beam to the rubidium atomic vapors and then probe with the potassium atoms. This type of hybrid OPM relies on the characteristic of the OPM relies on the densities of each atoms and density ratios. We try to measure the optimum density ratios recently, and we fabricated 5 different hybrid cells and compared the result, and also carried out simulations. I don't have enough time left, so I'll skip this part, but the measurement and the simulation show the good agreement. When temperatures of cell increases, the sensitivity also increases, but if the temperature is too high, sensitivity is going down, so there is optimum temperatures. In this case, density ratio of potassium and rubidium was 4.885. By the simulation, we can tell the sensitivity will be 1.6 femtotesla at around 270 degrees Celsius. And we also try to measure a multi-channel measurement using the hybrid cell. The advantage of the hybrid cell is we can obtain homogeneities all over the whole cells. So we created 5 centimeter cubic cell, and we tried to measure 20 channel. And we carried out MEG measurement with the 20 channel hybrid cell. Shown here is a result of the event-related desynchronization in 8 to 13 Hertz band. It is known as the alpha band. When subject open and closed eyes, amplitude of the alpha band changes. By using our 20 channel hybrid OPM, we could clearly detect this event-related desynchronization. Then I'll talk about a little bit of ultra-low field MRI. We try to measure the NMR, as one of the previous speakers explained. We fabricated our own ultra-low field MRI system and measured the NMR signal. We could successfully measure the NMR signal with this system. And we published MRI with this system as well in 2017. And then we fabricated a new, a little bit bigger ultra-low field MRI system, and then we tried to measure hyperpolarized genome using this ultra-low field MRI system, and we could successfully obtain the hyperpolarized genome image without prepolarization field. So finally, I'll talk about the future directions. By using the potassium and the rubidium spin exchange hybrid OPM, we can make OPM MEG and ULF MRI as well. And the future direction we are thinking is, the first one is a new fMRI, and the other is a new functional magnetic particle imaging. And then myelin imaging is important tool in the current neuroscience communities. So we also want to fabricate myelin imaging system in the future. To realize the functional MRI with the low field MRI, we have to use new principle to measure the cortical activities. This is the new fMRI principle to detect neuromagnetic fields directly by the spin look sequence. I'll skip this, but first we use the 7 Tesla high field animal MRI and tested this principle works, and we could successfully detect the signal change by the neuromagnetic field, like small amplitude magnetic field. And then we move on to verify the principle using the low field MRI. In this case, 0.3 Tesla MRI is used, and also we can detect the signal change. This is the final thing. We also try to measure the magnetic particle imaging. We could detect the same system to measure the MRI. We can observe clear magnetic particle signals. This indicates we can measure MPI signal and MRI signal simultaneously using the same system. Okay, that's all. This is a summary. Development of ultrasensitive OPM. We can realize innovative multimodal neuroimaging systems with high spatial-temporal resolution, which contribute for understanding human higher brain functions and clinical diagnosis as well. This is my students and collaborators. Thank you very much.